Last week, I tried to share how to fabricate the chips with all of you, and the major issue is called photolithography. And according to photolithography, we need to have such kind of layout. And I told you that such kind of layout will be fabricated layer by layer. So finally, you will see something very similar to this. This is some kind of three-dimensional view. And keep this in mind. All those layout actually is the so-called bird view from the sky, top down. Okay? So you have something like this, but you need always to remind yourself nothing is flat. Actually, all those layers, they are in different height. Okay? They have difference in height. So they can be overlapped. Something like this, the metal 2, the metal 1, but because they are at different layer, right? Even you have such kind of overlapping layout, they are not connected. You need what? You need vias or keep this in mind. You need to do it by yourself. And the other issue is you can see from this, for example, the top metal to the bottom metal, because there are quite many layers in between. Don't expect there is a via from the top all the way to the bottom. No, nothing like that, because we fabricate all those layer by layer. So from the top to the bottom, how can you connect them? Again, top via, the next to top via, all the way to the bottom. You need to do it by yourself. Okay, unless you get help from the EDA tools. Otherwise, you need to handle all those details. Anyway, let's go ahead. Oh, this is only some kind of simplification. Yeah. What I mentioned in previous week is much, much simpler than what really happened today. Okay? Even for those I show you, I don't think it is true for 0.35 micron or even older processes, because we omit some of the layers. For example, we don't show you the overglass to protect the whole chip, as I mentioned already. And I didn't show you the bonding pad. As a fabrication, how can you send your signal out or receive the input signal? You need such kind of I/O pads. We have two kinds of pads. One is for I/O, for input, to get the input-output signal, and the other to be connected to the outside world. And then we have something called probing pads. For what? For testing only. After fabrication, we need to make sure nothing going wrong. But how? We need to measure it, right? How to measure it? We still need to be, the chip still needs to be contact. So we need such kind of probing pad. However, after testing, all those probing pads won't be connected because they are useless. Only to make sure whether or not the chip is functional. That's it. If it is not functional, just throw it away. Right? If it is functional, then you need to do packaging through I/O pads. You need to have bonding wire, connect all those I/O pads to the metal pins, to the balls, to the PCB, as you like. And then allow me to have a brief review for what I told you last week. That is the so-called photolithography process. From the very beginning, we have wafer. Yeah. That is the so-called blank wafer, because nothing on the wafer. It is totally blank. It is empty, right? So after you get the blank wafer, you can do excitation from the beginning. Then what kind of layer you would like to fabricate from the beginning? You need to have such kind of photoresist coating, right? Spread the photoresist, spin the wafer to make the photoresist distributed as uniformly as possible. And then you need to have the optical mask exposed to the light, to the UV, EUV, DUV, any kind of UV, okay? If you have positive photoresist, then all those exposed to the light can be washed out. If you have negative one, then all those unexposed will be washed. Actually, yesterday, I Googled online to figure out that the positive one has better resolution than the negative one. Okay, the resolution, the accuracy. But why? Don't ask me. That is some kind of chemical or material. Yeah. Anyway, after exposure, we can wash out what you don't need. Then, yeah, we have such kind of photoresist development. Then etch away what you don't need. But with such kind of very dangerous, poisonous acid, you need to wash it. Clean it, sorry. You need to clean it, so you need to spin, rinse, and dry it. Then go for the next process again, and again. Finally, you fabricate all the layers. Then you get the final wafer. We call it patterned. Yeah, because you have all the pattern during layout on the wafer. That's it. Okay, that is the final step. But back to the origin. How can you get such kind of mask? Yeah, we need something called layout editor. I think the most popular ones are Cadence for Trousseau and Synopsys later. Alright, they dominate the global market. And this is the reason why when USA says no, then China companies will have a big issue. Because for EDA tools, to my memory, they dominate 90% of the global market. They're the best. And hey, look, I can get less than 10%. Get help from them. Oh yeah, but according to accuracy, much worse. Okay? The best not only dominate the market, but provide the most accuracy. So if you are talking about something less than 10 nanometer, I don't think for the race they can help Chinese companies to make it. No, definitely not. Okay? Not only for such kind of EDA tools, but also for EDA equipment. How about American companies? They dominate the market? No. Actually, for photolithography, ASML. In Europe, they call it ASML. In USA or United Kingdom, they call it ASML. So who knows what is right? Anyway, if you are talking about the best on Earth, we call it EUV, extreme UV, 极紫外线. ASML is the only company to provide it. So, can Chinese company get help from ASML? No. Why? Because when USA government says no, ASML wouldn't like to say yes. Sorry for that. Days ago, Chinese company sign a big deal from ASML, but according to accuracy, not EUV. As I mentioned, EUV you can only use EUV for something better than 7 nanometers. Above it, you need DUV, but deep UV. But the process will become very complicated. Right? Yeah, anyway. Not only for EDA tools, for equipment, for many of the others, just like chemicals, materials. So, till now, USA is still the strongest on earth. Again, when it says no, almost no Western companies would like to say yes. No. Sorry for that. Okay, you need such kind of layout editor you get help from this, but do the layout by yourself. Unless that is in digital domain, then EDA tools can help you finish everything. In analog domain, I guess almost 100% you need to do it manually through the help of such kind of layout editor. After you do the layout, on your screen you have, oh, this is my gate, and that is my source endurer, and all, right? On the screen, I guess the size will be at least centimeters, right? But how about the actual size? Oh, it will be scaled down all the way to micrometer? No, right now, to some nanometers. Wow. See? 7 order in difference. So you need somebody very good at optical management to scale down the size from centimeters all the way to microns to nanometers. Yeah. You need any kind of talented guys for help. Again, chemical, physical, mechanical, electrical, blah, 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 blah. All of them need to be integrated. Make the best on Earth, right? Okay, anyway, you need to scale it down from centimeters all the way to nanometers. We need such kind of pattern generator. Yeah, and then step and repeat the camera. To my memory, for each step, you can reduce to order. Okay, so from -2 to -4 to -6 all the way. You can guess how many steps you need to reach nanometers. So it is also very, how can I say, very expensive because you need to make sure during such kind of scaling down, right? You need to keep good enough accuracy. Otherwise, from the beginning, it looks like this. After scaling down, oh, it looks like that. You will have a big trouble with the fabrication, right? Right now, mask dominate the R&D cost. Maybe sometimes even more expensive than engineers. You need to pay for a lot. You need to pay a lot of money to fabricate the mask, even after layout. All right. So you need to be very cautious. You need to pay attention to all the details to make sure nothing going wrong. Otherwise, after you get the mask for fabrication, after fabrication, you figure out, it doesn't work. All the performance is really bad. Then, for small to medium-sized company, maybe one for all. It means one bad design for all to finish the whole company. The company may go bankruptcy. That is really dangerous. So right now, very few companies can enjoy the best process. Just like right now, 5 nanometers is the best, right? Who enjoy it from the beginning, Apple, and then Qualcomm, MediaTek, blah blah blah. Even from the very beginning, MediaTek usually one process behind Qualcomm, and Qualcomm one process behind Apple. Apple the first, then Qualcomm. Maybe in the past Huawei or the others, but right now, yeah, I guess after Apple, MediaTek would like to get the newest process because it has enough money right now. Okay, let's go for it. How to do such kind of layout? I mentioned already, you need such kind of symbolic mask layers. If you go back to see this, something very close to the real situation. All the metal layers, they have the same color. How can you do such kind of bird view layout? Oh, it's really hard to distinguish among layers, right? So even they are made of the same material, you still need to have different color, different pattern to differentiate all of them, to make them look different for layout engineers. Otherwise, I don't think anybody on earth can do such kind of layout. Right now, how many devices? It's already more than 10 billion. Oh gosh, 100 亿. Okay? And how many wires? Much more than this. All of them are gold. All of them are golden. Right? Just like copper wire. Wow. It's really complicated. Beyond our capability. So we need to have such kind of symbolic. It means it is not real. Only some kind of virtual layer, some kind of representative layer, they are not real. Okay, so they are abstract, 抽象的. Why we don't have some kind of real layers? Sorry, I told you already. Many of the layers, they are made of the same material. They are exactly the same. How can you differentiate them during layout? No way, right? Anyway, you can see, metal one is blue. Oh, is it blue? Copper metal one? No, sorry for that. But this is only some kind of abstraction, some kind of symbolic. That's it. So you can easily differentiate this from that. Okay, so poly is red, N plus is green. But why? Metal one needs to be blue. Can it be yellow? Can it be red? Yes, as you like. We have something called layer map table. Later I will show you. Layer map table. To map the real one to the abstract ones. Okay? Who is what? Which is what? According to layer map table, you can tell all of them. Can you modify it as you like? But especially on campus, we have the default layer map table from our NSRL, okay, our interface CIC. But how do they set the rules for layer map table? By default, I guess they get everything from TSMC, UMC. So don't swap them. TSMC's layer map table is totally different from UMC's. Don't make any trouble for yourself. Okay? If you would like to change it, maybe you work for MediaTek, such kind of biggest IC design house in Taiwan. Yeah, you can change it, but after changing, before fabrication, you need to show the new layout map table to TSMC or UMC. Otherwise, they will have wrong fabrication for you. Okay, as you like. So this is some kind of example of polyethylene, only for a good example, but not real. Okay. According to the layout map table I show you, metal one is blue, poly is red, all of them, and finally you will see this. Okay, yeah. So you can see, if somebody has such kind of monochromatia, it means color blindness. They cannot serve as not only medical doctors, but also layout engineers. So you can see how important layout engineers are. According to this, they are as important as the medical doctor. But according to income, they get much lower ones. Yeah, for a little bit better process than the one I showed you in last week. For example, you have such kind of dual well, or sometimes we call it twin well. It means two, right? Dual or twin. Sometimes we don't call it well. Sometimes we call it tub. Okay? Yeah, anyway, I feel like I don't care. Why we would like to have some kind of dual well, twin well process? Simply because you can see, this is NMOS in P well and PMOS, right, in N well. Wow. Or what? Actually, if you would like, you can get rid of the so-called body effect. Okay? For the usual ones in Taiwan, we have NMOS in P well, then P substrate, right? We don't, sorry, no. I pointed at the wrong one. We have such kind of PMOS in N well, then we have P substrate. We don't have such kind of P well. Alright? So it really means what? For NMOS, usually cannot get rid of the body effect. If you would like to get rid of the body effect, you need to connect your body to your source. Right? So for such kind of P substrate process, yeah, for the bottom NMOS, you can connect the body to the source. And how about the one above it? You can connect the body to what? Because all the bodies are P substrate, right? So you can only connect it to here then to the ground. You can connect it to the source. If you connect it to its source, then you can see this source is connected to the body, but all the body are right. So it means what? This one is shut up. Its source is to the ground. Its strength connected to this source. This source is also connected to the ground. Wow. So it is not functional at all. That's it. Sorry for that. So it means for some dual well process, in theory, it can provide you better performance. But nothing is free. You need to pay for it. To isolate all those P well, and especially P well and P substrate, right? You need somebody for isolation. You need another layer called P epi. Okay. Yeah, the conductivity is really low. And above it, you can have your N well, you can have your P well as you like. So money talks. But you can say, hey, Tiana, do you have such kind of very close to dual well process? Yes, especially for SOI. Yeah, silicon on insulator, right? You need some kind of insulator to have such kind of better performance MOSFETs. Yeah, anyway, in theory, for the same technology, SOI in performance is better than the so-called bulk process. That is the mainstream. Bulk process is the mainstream for TSMC, UMC. SOI, who is the best in the past IBM? Then maybe Global Foundry and also Samsung, maybe. Okay, Intel. Both. Here or there. Yeah. Anyway, for TSMC, usually they before FinFET, they dependent on bulk process very much. For mass production, they wouldn't like to touch SOI. Why not? They would like to get better performance because it is so expensive. More expensive, not too expensive. With the same money, you pour the same money into here or there. This one will get faster development. So you can see if I get 5, maybe you only get 7 or 10. Right? So 7 to 7, this one is better. But you are 7, I am 5. So for overall performance, I am still better than you. That is the logic thinking for TSMC. Okay, yeah. And allow me to show you some kind of real transistor. This is from Bell Lab. In the past, they are also very strong at fabrication, but right now they are nobody. Yeah. For such kind of 0.25 micro, actually the feature size is 240 nanometers instead of 250. Anyway, how to capture a tiny transistor? Then you have such kind of cross-sectional cut, right? And then show all the detail on the microscope. It's really hard. Okay. Anyway, anyhow, allow me to show some detail for you. This is the poly. Okay. And this is the channel substrate. They are connected together. They are of the same kind. In between, you have silicon dioxide, gallium oxide for insulation to separate, to isolate your polygate from your channel. They cannot be connected. So to both sides, you have source or drain. I don't care which one is source, which one is drain, because for such kind of regular transistor, in theory, they are symmetrical. Okay? But allow me to show you the very important idea. This is the edge, one of the edges of your polygate, right? But you can see, below it, your source and drain doesn't align with the boundary, because for drawing, for layout, it looks like that. So the boundary, one of the edge is here. So in theory, you may guess, how about the area for this source of this drain? In theory, it needs to be aligned here, right? 他们需要在这边切紧 but it is not true. It never be true according to site diffusion. Here, it's really apparent. You have such kind of huge site diffusion. So I guess the source and drains were doped by diffusion instead of implantation. With implantation, the site diffusion will be reduced very much, but it never be reduced to zero. No, sorry for that. Okay? So you have site diffusion here, you site diffusion there. So for the length you draw from, you may think, especially for new engineers, you will think, from this edge to that edge, that is the length I draw. But after fabrication, what is the real length? Sorry, real length is from here to there. Okay? So the real length is much shorter. How can I say much shorter? According to diffusion, it is shorter than the length you draw during layout. For implantation, a little bit less, a little bit shorter than the length you draw. That's it. You need to keep this in mind. Okay? And then, on the surface of the polygate, you have something very black. What is that? Metal layers. We try to diffuse some kind of metal atoms inside your silicon crystal. For what? To enhance the conductivity. So we call it silicidation or salicidation later. I will explain. Okay? Similarly, to enhance the conductivity of the source and drain, you have this and that. The black ones are what? Metallic atoms. 金属原子哈，被塞进去，金属化合物了啊，提升它的导电度。Okay, allow me to show you some of the real micro photos. Oh, this is not real. That is some kind of plots only. And that are real. This is from IBM, to my memory, and this is from what source? I have no idea. But I would like to show you. After fabrication, if you zoom in to get enough detail, oh look, you have chimneys, right? You have a lot of high buildings. You have buses. Oh, very similar to humankind's construction, right? Just like something you can see in the airport, in the sea, around the seaport, in the big city. Yeah, not exactly. Much, to be honest, much more complicated than our real cities. Yeah, I'm not only talking about Taipei. No, the structure will be much more complicated than Tokyo, than New York, than London. Okay, allow me to show you some more detail. As I mentioned already, for metal layers, from the top one to the bottom one. Okay, how can you connect them? No via, no single via to make it. So you can see from metal 4 via metal 3 via metal 3 via metal 2 via metal 1, and then contact to connect all the layers below metal 1. I don't care any kind of layer below it, just like gate, soul, strand, body, blah blah blah, all of them. Below metal 1, it is called contact. Above it, above metal 1, we call it via. But in theory, they are made of the same material right now, copper. Okay? Yeah. Oh. The other important issue is this. Dimples. 9. You can see above the surface of the via or contacts. Something goes wrong. Is it good for you? No. You can see for high frequency current, right? They conduct from here to there. They will be scattered by such kind of impulse. So you can see the surface look like this. Right? Is it good for conduction? No. We hope it is totally flat. But we are humankind. We are not gods. We cannot make anything like that. We can only make something like this. Got it? So it means what? The wider opening, the more impact from impulse. If you have wider opening, this is the original opening. If you have such wide, then the dimple will look like that. Even worse for conduction. Got it? And this is the reason why, for contacts of vias, we always use the smallest size and as many as possible. Okay? That is one of the main reasons for the via contact layout. It means we don't have such kind of huge or such kind of large rectangle, large square for contact of vias. No, sorry for that. According to DRC, you always need to have something like this. Use the smallest one and as many as you like. My recommendation is as many as possible. Later I will explain why. Okay, so according to the smallest size, the dimple impact will reduce to the minimum. Not only this, for high frequency conduction, that is the most. Okay? According to the resistance. Yeah. If you have such kind of huge one, you can say, hey, I have this huge. And then I have small ones, smallest altogether, right? Which one can provide the best conduction for high frequency operation? I promise you, this one. And for this, it will provide you very terrible result. Because according to skin effect, 肌肤效应. Okay? During high frequency operation, this one doesn't make any sense. The high frequency resistance will increase substantially. That is really bad for our chip operation nowadays. Okay? Then let's go for even better one. This is the so-called FinFET. It is three-dimensional. And for all those I show you, they are flat. We call it two-dimensional. Okay? So, what is the boundary for 3D and 2D transistor? Around 20 nanometers. Before it, we used two-dimensional. After that, smaller than 20, we use FinFET. Okay? But don't be too happy. Will we use FinFET all the way to 3 to 2 to 1 nanometer? No, sorry for that. According to the roadmap of TSMC, FinFET will survive until 3 nanometer. But for 2 nanometer, they will use the other one called GAA, gate all around. Now later I will explain the structure. Okay. However, for Samsung, it would like to compete with TSMC. It would like to have some kind of how can I say? Anyway, according to Samsung, it will apply GAA for 3 nanometer process. Okay. TSMC postponed GAA to 2 nanometer. So who will win? Let's wait and see. Okay? Because the strategies needs to be different for Samsung. Because if you follow the roadmap, if you follow the steps of TSMC, you are already fine. Okay? How can we go beyond? The strategy needs to be different. Use the better structure to defeat TSMC. However, it is much more complicated for fabrication. Okay, that's it. Let's wait and see. Alright, allow me to show you this. This is some kind of three-dimensional structure, three-dimensional FinFET structure for Intel only. For TSMC, actually, the structure is not the same. Okay? Maybe more than 10 years ago, some Canadian company called Chipwork, it has such kind of reverse engineering to figure out one portion, a tiny transistor, to get such kind of cross-sectional view. Then the company was sued by Intel. Intel said, don't reveal any detail to the others. Okay? Otherwise, I sue you. So, Intel sued Chipwork, but to my memory, it failed. Yeah. Anyway, it is not any kind of patent. Yeah. And how about TSMC? To my memory, it doesn't have such kind of shape. No? Right? That is for Intel. And how about TSMC? Yeah, maybe much closer to this. That's it. Okay? Yeah, anyway, anyhow. What do they want? With such three-dimensional one. Yeah. If for two-dimensional one, if you squeeze it to make it flatten, then what is the width? Only from here to there. That is the definition. Okay? You have such kind of, and you, above it, you have, that is two-dimensional. This is a gate, source and drain, right? So what is the width? Only here. What is the length? There, right? So width here, from this side to that side. So according to the two-dimensional view, right? The width is only from here to there. But you can see this is a new one. The equivalent width is from here all the way to there. Okay? That's it. Yeah, this is gate. Sorry, this is gate, and this is source and drain. So the width will become such. Okay, reverse V shape. It is much better than two-dimensional one, right? That is the logic thinking. Why? FinFET operate faster than two-dimensional structure. Okay? That's it. And how about the length? This is source, that is the drain. So the distance here, that is length. So the length is here and the width is there. Something like that. Okay? So we would like to increase. For this one, it is almost not possible to reduce the length, right? So from two-dimensional to three-dimensional, we would like to increase it instead of reduce the length. Okay? But the main target is still to increase the conduction current. That's it. Yeah. So it means what? For humankind, we already use out all the ways to reduce the length. So we cannot make it further, right? We would like to enlarge the width. That's it. From 2D to 3D. Then, from FinFET to gate all around, again, because length was already minimum for humankind, right? So from 2D to 3D to enlarge W, right? And how about 3D FinFET to gate all around? To further increase W. That's it. No secret. Later I will to the end of the three-dimensional plot. Make it even clear for you. Alright? Yeah. Then for according to our history in the past, we have aluminum for interconnect. But according to conduction, copper is much better than aluminum. Why? Humankind used aluminum in the past for metal knives. We didn't know how to fabricate copper along with silicon. The major issue is if you would like to diffuse, if you would like to deposit any kind of copper layer above silicon, the copper atoms will diffuse into the silicon structure. Then it is very hard to control the width or length. Okay? That is a really upset phenomenon. So, how to stop such kind of chemical reaction with silicon? I mean for copper. The copper will have such kind of chemical reaction. So it is really hard to fabricate copper above silicon. That's it. That is the key idea. But don't ask me why. I am not any kind of material guy. Don't ask me. Okay? I would like to only show you the history. So how to stop such kind of chemical reaction between copper and silicon? IBM. Again. It is the one to get the first idea. It needs some kind of help from this, the so-called, because IBM nobody would like to tell you what kind of chemical can stop such kind of reaction, because it means a lot of money, right? So allow me to show you this, some kind of silicon layer. I don't care, monosilicon, polysilicon, or silicon dioxide. Sorry for that. Copper will always interact that. That is really upset, right? So to stop such kind of reaction, some secret chemical. What kind of secret chemical? Don't ask me, okay? From the beginning, only IBM knew it. So after you deposit such kind of secret chemical, then no reaction between the copper and the silicon layer, right? So you can have photoresist above it, exposed to the light, blah 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 blah. So finally, you can fabricate very good carbonite. That is the secret from IBM. Okay? And when it happened to the last half of 0.80 micron, it means that from the beginning, 0.80 micron is still used aluminum for metals. But to the end, everybody changed from aluminum to copper through the help of IBM. But you need to pay for it. Sorry for that. Okay? That's it. And also you can see, for dielectrics, if you are talking about current conduction, again, alright, let's go back here. According to this one, right? To speed up the operation, we would like to enhance the current conduction. So never mind how hard you try. You get the widest style, you get the shortest length, blah blah blah. And after that, what you can do? We can enhance this one. Okay? But how? Electric constant. Right? The more epsilon 介电系数, the more C oxide. Alright? Yeah, I think I explained already what is C oxide. Actually, it is this divided by distance, the thickness of your gate oxide. Okay, so we reduce WL and the gate oxide thickness to the minimum already. Or we enlarge the W already. Then how can you enhance the conductivity? Epsilon. The more epsilon, 介电系数, okay, dielectric constants, the more C oxide. But how to make it? If you have pure silicon dioxide, because it is made of silicon dioxide, okay? For silicon dioxide, the common insulator for chips, from the beginning, the constant is only 3. For pure silicon, to my memory, it is around 13. So it means what? If you diffuse some impurity into silicon, the dielectric constant will be changed substantially from 13 to only 4, right? So we can do the same thing to diffuse another kind of atoms inside silicon dioxide to increase the dielectric constant. It is good for what? Conduction. But between layers, metal 1, metal 2, metal 3, right? Metal 1 here, metal 2 there. It also has such kind of capacitance, right? But it is parasitic capacitance. We hate it. Again, to speed up the operation, we would like to reduce the parasitic constant, right? The parasitic capacitance. So it means what? Between the gate and the channel, we would like to enhance epsilon. But for all the others, between layers, we would like to reduce it. So we need to have the so-called low K and high K. We are all talking about silicon dioxide, but with different impurity. One is to increase the dielectric constant below the gate. to enhance current conductivity. And for all the others, we would like to reduce the dielectric constant to reduce the parasitic capacitance. Got it? That's it. So, even for the same process, we have low K and high K silicon dioxide with different impurities. That is what we need. Okay? And then for optical problem, I can stop here. But because I mentioned already DUV, EUV, blah, blah, blah. So allow me to show you some of the truth. From the very beginning, we have UV for photolithography. According to wavelengths, it has almost 250. So that is close to 0.25 micron, right? Above it, no problem at all. I mean, for 0.35, for 0.5 micron, even for 1 micron, 2 micron, no problem with this. But with smaller feature size, okay, according to optical, with some kind of optical problem, right? If you have the so-called slit, 细缝, a slit, just like here, for the wave to penetrate, right? If the wavelength of the light is smaller than this, no problem at all. But larger than this, longer than the width of the slit, then you will have some kind of the so-called. Got it? Yeah, that's it. That is the biggest problem. Okay, so if, for example, this is the slit, okay, then the light gets in, hopefully it goes through all the way. Then what you see will be what you get, because this is your photo mask and you have photoresist here. Yeah, this white will become that white here if the light go through directly from here to there. Congratulations. But you need to make sure the wavelength of the light needs to be smaller than the width. So with UV, it is only 0.25, right? So with UV, to fabricate 0.25 or before, even for 0.18, it is still good enough. Not so bad. However, if the wavelength becomes longer, or no, it is not become longer. If the slit become narrower, right? Much smaller than your wavelength, then sorry for that. The wave don't go all the way down. No, they have diffraction. Okay? So what you see never be what you get after exposure. That is a big problem. But we try to narrow down the slit from 0.35, 0.25, 0.18, all the way to 5 nanometer, 3 nanometer. What you can do? You need also to reduce the wavelength for your light. That's it. Okay? To prevent such kind of diffraction. 绕射. Got it? So we try to replace UV with DUV. However, DUV is only 193 nanometers. It is no good for nanometer fabrication. Actually, to my memory, DUV can be used for almost to 10 or even to 7 nanometer. Okay? So the biggest Chinese company for fabrication, actually, I told you days ago, it got a big deal with us more, but only for DUV. Okay? It's allowed to sell EUV to China. by USA government. Alright, so what is the wavelength for EUV? Aha, see? Only 13.5. So it can be used all the way to my memory. 3 nanometer at least. For 2 nanometer, I have no idea. But definitely for 1 nanometer, sorry, EUV, current ASML EUV machine is still no good. Okay? You need to get the newer one, better than this. That's it. That's it. Yeah. So, I help you to update this information. In last year, ASML shipped 31 EUV systems. Globally, only 31. Okay? Yeah. The overall TSMC, to my memory, overall, not only for last year. I mean, from the beginning. Last year, TSMC got 36% of the EUV machines. And how about its strongest competitor, Samsung? 31. You may say, hey, 31, that's so bad. Oh, sorry. Because 31 is not only for chip fabrication, but also for DRAM fabrication, blah, blah, blah. Okay? So, if you are talking about such kind of fab for fabless IC design houses, Samsung, according to such kind of 31% of market share, maybe more than 50% went to DRAM fab, went to flash memory fab. So, to help Qualcomm fabricate chips, maybe less than 10%. So this is the reason why for 5 nanometer, because it has much less EUV machine. For TSMC, all of them, to help the others for chip fabrication. Okay? And this is the reason why I have more machines for you for trial, and then for mass production, I can produce much more than you. And I can achieve much better performance than you because I have more machines to try. That's it. Okay? Oh, the other sad story for Intel. Intel in last year canceled all the EUV machine from ASML. I have no idea why. It canceled the deal, right? Then TSMC and Samsung become crazy to capture all the EUV machines. Wow. This is a really bad story for Intel. Yeah. Right now, it is far behind TSMC and Samsung for such kind of chip fabrication, according to wrong policy. I don't know why. You would like to cancel EUV machines. No idea. Okay, allow me to show you some kind of roadmap among the biggest companies on earth. See, Intel from the beginning was the best. Till what? You can see, hey, look, even right now, it has 10 nanometer, but I told you, Intel's 10 nanometer in performance almost equivalent to 7 nanometer of TSMC. Right? So it's still a little bit better than TSMC because 10 nanometer Intel here and TSMC 7 nanometer there. Right? Right? But after that, right now it's still 10. They said maybe in next year, not in this year, maybe in this year, they will provide such kind of 7 nanometer process. And in performance, maybe it is only equivalent to 5 nanometer of TSMC. So where is 5 for TSMC? Here! Okay? It is already went for mass production in last year. So the fact is for Intel is in this year, or maybe in next year. Oh, here to there, 2 years behind TSMC. And this, it means what? Intel will have a biggest issue since it is founded according to manufacturing. It is not the biggest issue for Intel only, but also for the whole American. So according to President Biden, yeah, he would like to support the semiconductor industry in America. So it means USA government will pour a lot of money to support, but not only for Intel. Because TSMC would like to have a new fab in USA, right? It can also get a lot of sponsorship from Biden government. It's really good. I heard that Samsung would like to do the same thing. Oh, let's compare Samsung to TSMC. You can see what's going wrong for TSMC. Where is Samsung? Samsung is here, right? Oh, sorry. That is too new. Before that, Samsung launched 14 nanometer. Okay? About the same time, TSMC only launched 16. So it means some years before this, Samsung led TSMC for fabrication. But I told you already, even with Samsung 14 nanometer process, the performance is worse than 16 nanometer from TSMC. It doesn't make any sense. Since after TSMC led Samsung for any kind of fabrication. So you can see, here, TSMC 7 nanometer, right? Where is Samsung? There, right? And 5 nanometer here, Samsung is there. According to performance, TSMC's 5 nanometer is better than Samsung's. Okay? Yeah, anyway, you can say, hey, Samsung announced such kind of 4 nanometer. Actually, TSMC have, for 7, it gets 7 plus. Alright? And then 6. They are of the same kind. With some kind of enhancement. So how about 5? TSMC have some kind of 5 plus. And then 3. Okay? So they are different. From 5 to 5 plus and 4, they are of the same kind. And then 3 nanometer is different. Alright? Anyway, I told you already. You may say, hey, look, TSMC looks in danger. Oh, that is only roadmap. But for TSMC, it announced that the process for 3 nanometer is beyond. Okay? Yeah, it get better progress than the roadmap. And according to Samsung, it got some bad news. 1 quarter lag. Okay? So for TSMC, maybe 1 quarter or 2 quarters beyond. And Samsung, at least 1 quarter behind. So totally, you can see the difference, okay, between TSMC and UMC. That's it. Okay, we can have a break right now. I hope this is a good story for all of you to learn not only something, but also to know the story, okay, to know the story. Then you can make your decision to join TSMC, Intel, or Samsung as you like. And for others, they are far behind. You can see, Global Foundry, right? They stop here. They don't go further because it is too expensive. And how about SMIC? SMIC is the biggest Chinese company for chip fabrication. days ago got a big deal, okay, from ASMO, but only for DUV, no EUV at all. Alright? And UMC, the second in Taiwan. All stop here. No further. Alright, that's it.